My name is Ann Wood. I am a cosmochemist here at NASA Johnson Space Center. I'm a co-investigator on the OSIRIS-REx mission. And also, I was participating scientist on JAXA's Hayabusa 2 mission. So last year, we were fortunate enough to be able to get a little piece of Ryugu and analyze that asteroidal material here. So I'm the director of this lab. This is a NanoSIMS lab, and SIMS stands for Secondary Ion Mass Spectrometer. So what this instrument does, it allows us to determine the isotopic compositions of samples. And it's a NanoSIMS, so it has nanoscale spatial resolution. So we can measure grains down to 100 to 200 nanometers in size, and also study fine scale features across the sample. Other instruments like this have spot sizes of like 2 to 5 microns, so a really large beam compared to this instrument. So we can really get into the details and study individual grains within these samples. So as I said, we studied Ryugu samples last year, and that workflow that we're discussing with you today will be applied also to the OSIRIS-REx samples as well. So this is asteroid Ryugu here, and you might think, it looks a lot like asteroid Bennu, which it does. So there are a lot of similarities between the two asteroids, but also some differences, and really excited to see how the two asteroids compare. So let me just walk you through some exciting results that we just published in Science Advances a couple weeks ago on our studies here. So we performed these coordinated analyses on the Ryugu samples. This is how the sample is prepared and comes to us, one way of preparing them. So these are millimeter-sized fragments of asteroid Ryugu that are pressed into metal. The surface has to be really flat for this instrument to work properly. And here is one of those millimeter-sized fragments. So the first step after the sample is prepared is it goes into the SEM lab, and we prepare chemical maps of the samples. And later I'll be honing in on this small region here. So as we're moving from instrument to instrument, we kind of go down in scale, finer and finer and finer. So this is an example of those chemical maps taken in that SEM right over there. This is a backscattered electron image of the sample and corresponding oxygen, magnesium, silicon, iron, and sulfur elemental maps. So this region outlined in white, and also this little, I call it Italy here, are called clasts, and we found them to be chemically different from the rest of the Ryugu sample. So if you can see, it stands out in the magnesium image. It's depleted in magnesium, enriched in sulfur, depleted in silicon, enhanced in iron. So, we thought, hey, this little class is very interesting chemically, so what other secrets does it hold? So then I take that sample and I put it in this instrument, and I can obtain isotope maps. So here are some of those maps. This is oxygen 16, for instance, silicon 28, and this region in particular has that clast I was just talking about on the left-hand side, and on the right-hand side is the Ryugu matrix. So you can already tell in this image they look very different from each other. So the class is very fine-grained. The matrix has been hydrated, very, very hydrated, so it has a lot of phyllosilicates. And in the silicon, you can tell, again, it's quite stark, the difference here between these two materials. Also, in the carbon map, and this is a nitrogen map, another thing that stands out is the clast is really enriched in organic matter. So the nitrogen is associated with organic material. So Ryugu is already a very organic rich asteroid, and this clast material within it is even more organic rich. And I forgot to mention, but these clasts are like 60 to 100 microns in size, so they're very, very small. So So next, we can also look at isotope ratio maps. So we can, through these maps, see grains that are isotopically very different from the rest of the material. And Lindsay mentioned stardust grains. So this is a carbon-13 to carbon-12 isotope ratio map, and this is oxygen-17 to oxygen-16. So most of the material has the same isotopic composition, but this particular grain here and this particular grain here kind of lights up in these images, and these are stardust grains that have very different isotopic compositions. And how they get those different isotopic compositions is they come from other stars that are much more evolved than our sun. So when a star evolves, the isotopic compositions and the chemistry changes within the star, and these grains form from that gas from that star. And so these grains were transported for millions or billions of years through interstellar space, and they were incorporated into these primitive asteroids and comets, and they're preserved in the ones that don't have too much alteration to them. We can also look at organic matter. These are hotspots of organic matter that are enriched in nitrogen-15. And that's an isotopic signature that points to formation in the cold interstellar environment. So these stardust grains and this organic matter are, the material that built our solar system. So they're the starting materials. So we found in this class, again, it was chemically distinct from Ryugu material, but it also had exceptional abundances of these stardust grains and primitive organic matter. So it's a very, very primitive class. So again, after I analyze the sample here, and I say, hey, this is a very interesting piece of stardust, what is it made of? And so then we take it to the focused ion beam lab down the hall, and we carefully prepare these electron transparent, very thin cross sections of the grain. So this is just showing the preparation of that sample, and the tiny target grain, 2 to 300 nanometers in size, is in here. And then Lindsay can then look at it in the TEM and determine its chemistry and its mineral structure. And what we learned from that is, for this stardust grain, is what was the chemistry of the stellar environment in which it formed, and what did it undergo when it traveled through space to get here, and what happened on the asteroid, that housed it. What kind of processes happened there. So we get a lot of information about the sample, its history, and its origin, and we can't wait for our OSIRIS-REx samples. All right. Anybody have any questions? Or if not, Eve Berger is up next.
Hi everyone, I'm Eve Berger, and I'm an organic geo and cosmochemist. We're not going to go upstairs to my lab right now because it's a little bit too noisy and too small for this many people, but if anyone would like to see it afterwards, we have a couple minutes. I can walk you up to take pictures, or at the end of the day, before you all leave, we can do that. So if you want to see it, just ask. I'm happy to bring you up there. So I was a grad student at the University of Arizona when OSIRIS-REx was being written, and I'm super excited decades later to actually be on the OSIRIS-REx team. So one of the more than 200 scientists from 35 institutions across the globe that are going to be part of the science team studying these samples coming back. I also do some of the contamination control studies, and I'll also be part of the field retrieval team, picking up environmental samples. So I'm a backup on that team for Francis McCubbin, who's also at JSC. So I'm super excited about that. We were out practicing last week in the field. But OSIRIS-REx is bringing back pristine samples, and for me that's super exciting because I want to study the origins of life. So what material gets brought to the Earth, delivered by asteroids and comets, and what happens to it that, it turns into us eventually, right? So I kind of think, I do experimental work looking at the really early stages of that process, and I want everyone to think of their favorite dessert. Think of the restaurant you go to. It's like that perfect sweet bite of food after a meal. You go home and you say, I could totally make that. I can reverse engineer that recipe. I know what was in it. It was flour and eggs and sugar, and maybe a little ginger, maybe a little cinnamon, could have been a little nutmeg, but I'm not totally sure, right? Because you don't have that recipe at home. OSIRIS-REx is bringing back samples that haven't seen the Earth. They haven't seen us, they haven't seen our atmosphere, so they haven't been contaminated by the Earth. So this is like an ingredient list from a 3-star Michelin restaurant, right? The original recipe. And so we take that information. So I study these grains and I pull out information about amino acids, and then I characterize also using the SEM and the TEM that Lindsay described for you earlier to talk about the mineralogy that these amino acids are in. And those two things together are ingredients, and it tells us about our process. So geothermometers, geobarometers, so temperature and pressure. It tells us how long stuff has to be in the oven and what kind of oven we need. It might be we need to bake it outside. It could be it needs to be in solution. So all those kinds of things can be gleaned from these pristine samples that are coming back. The other thing that I'm super excited about, well, before I do that, I'm going to teach you all a little organic geochemistry because everybody should know something about amino acids. So one of the reasons that this is an interesting problem is amino acids are, some of them are chiral molecules, which means they exist in two forms that are mirror images of one another. So kind of like your hands, and they are non-superimposable. No matter what you do, you can't get your hands to be identical one on top of the other. And for amino acids, this means that they behave differently in chemical systems. Life here on Earth only uses L amino acids. Meteorites deliver both L and D. And so how did we go from L and D to just L? And you can imagine having a really pristine sample that we haven't added a little L to. It would be a wonderful, just a wonderful sample to have. And I guess I'll end by just saying that, think about this mission. Less than 3 years ago, these samples were on an asteroid traveling through space. It had been there for over 4 billion years. And in less than 2 months now, because it was 2 months earlier this morning, they're going to be on the ground in Utah. And we are going to get our little fingers, not really on them because we're going to keep them clean, but we're going to get to analyze them using hundreds of different instruments. And if we can unravel what happened here on Earth, it gives us an idea of where we should look elsewhere in the solar system for where there might be signs of life or organic molecules. And with that, I'll take any questions or walk people upstairs for a tour, whatever's best.
Yep, let's go up the stairs. Can you tell us more about the equipment over here?
Anne can tell you more about the equipment here.
Yes.
What
I mean,
would you like to know?
it looks interesting, so I'd like to,
Know how it works?
Yeah,
kind of the
yeah,
basics
yeah,
of
if you
it?
don't mind.
Okay, so let me just kind of show you here.
Hope so.
So this is where the primary source is. So we have two types of sources in this instrument. We have a cesium source and we have an oxygen source. We need two of them because we want to analyze isotopes that come off as positive ions and also isotopes that come off as negative ions. So that's why we have two different sources. So the source comes down to here, the primary column. The sample sits in here. So here's, if you have your sample here, your primary ion beam can sit at, 90-degree angle. And then secondary ions are ejected from your sample. The process is called sputtering. So the primary ion sputters away at your sample, and then isotopes are ejected from that sample. Those ions travel down the secondary column. You have an electrostatic analyzer, which focuses your secondary ion beam in terms of its energy. And then it goes through a big magnet here. And what the magnet does is it separates the masses of your ions coming down. So this instrument has 7 small detectors on it, so it can analyze 7 different isotopes at the same time. And this is really important, when you have a grain that's 200 nanometers that you want to analyze. As I said, the primary beam is sputtering your sample, it's eating it away. So you want to collect as many isotopes and ions as you can before your sample is gone. Potentially it could be gone. Hopefully not, because then Lindsay can look at it. But yeah, so it's really important to measure as many isotopes as possible and gain as much information from these small samples as possible.
Okay, thank you.
Yeah.
That's
Yeah,
really
you're
cool.
welcome.